Hello, welcome to this video. In this video we are going to discuss a simple example for normal subgroup of a group. Here we consider the set of all 2 by 2 matrices. See the set of 2 by 2 matrices GL2 2 stands for the order, and the matrices GL2R. R stands for the real numbers, set of real numbers. See, this is the group GL2R, and then its subgroup is SL2R. SL2R contains all 2 by 2 matrices with determinant 1. But GL2R, the group GL2R, it contains all 2 by 2 matrices, which contains its entries real numbers, but with non-zero determinants, or having non-zero determinants. Since the matrices here included in this group, in this set, are have non-zero determinants, of course these elements have inverses, and their inverse exists, and those inverse also then belongs to this set. Yeah, it is very clear that the inverse belongs to that set because it's a group. We have or earlier we have seen that both access groups both behave like groups. Okay, so it is now clear that this set, this group, is a subgroup of SL2R. SL2R, the group SL2R is a subgroup of GL2R, and we want to show that SL2R is a normal subgroup of GL2R. Okay, for that we can use for establishing that it's a normal subgroup. SL2R is a normal subgroup of GL2R. We use the method of we use the definition of a normal subgroup. We use the method of definition of a normal subgroup. That is that's direct way. For that, we know that a group is a subgroup is a normal subgroup of a given a subgroup H of a group G is a normal subgroup if xh equal to hx for all x belonging to G, for arbitrary x belonging to G if xh equal to hx. So that method we can follow here. So for that, let's take an element of GL2R. Like we take an element capital X. So since it's a matrix, an element means it's a matrix, therefore we use capital X. Capital X belongs to GL2R. Here it will be denoted by G. Here it is G, the mother group, and then we take an element A. It's an arbitrary element. See, this element must be element A must be an arbitrary element, arbitrarily chosen from H. Let A be an arbitrary element of H, and X, so X must also be an arbitrary element of G, because we have to test it with every element of G. So X is arbitrarily chosen from G, and we choose A arbitrarily from H. But determinant of A equal to 1, but determinant of X is not equal to 1. It is not equal to 0 also. So see, it may not be equal to not always equal to 1, but it is not equal to 0. That's important. And after that, we consider we take, since we take xh x inverse, since we consider xh x inverse for every element where the middle element xh is the that subgroup. So we can test it by considering arbitrarily an element, by choosing arbitrarily an element from H, and for that we are choosing A arbitrarily from H. So we take x a x inverse. See, this x must also be a capital x. This x is capital. In the same way, this x must also be capital. So x we take the product x a x inverse, x a x inverse, and after that we consider the determinant of x a x inverse, because the membership of the product or the matrix, membership of the matrix will be determined by will be decided by the value of the determinant, whether it belongs to H or it belongs to G, and all these things are determined by the determinant. So we have to find the determinant of the product x x inverse, and then applying the determinant to this product, we get the determinant of x into determinant of a into determinant of x inverse. Actually it is determinant of x inverse. Then we get that it is determinant of x the whole inverse, because determinant of x inverse equal to determinant of x the whole inverse. Determinant of x inverse. Okay, and then what we can substitute here, determinant of a, we know that since a belongs to H, determinant of a equal to 1, and therefore you can substitute 1 there, the middle part, and then we get the determinant of x into it, then reduces to a determinant of x into determinant of x the whole inverse, but finally it becomes determinant of x into x inverse. And but you know, x into x inverse, because since x inverse is the inverse of x, it is the identity element here, determinant of identity element that equal to 1. And finally this shows that the product x a x inverse has determinant 1. That means that this product x into a into x inverse must belong to the set H, the subgroup H, and hence we get that whenever we take arbitrarily an element from G and arbitrarily an element from H and find the product and take the product x a x inverse, and then we take the determinant, we get that its value equal to 1, and implying that x, the product x x inverse belongs to H. Therefore H is a normal subgroup of G. Okay, this completes our verification. Thank you.